This is a video editorial for the LeetCode weekly contest 484. This contest I felt like the first three problems were fairly easy. Q4 I found interesting because this was the first time I saw this pattern, but apparently this problem was a repeat as well. So I'll link the timestamps for the different explanations and the portion where I live solved the problem, so you can watch me struggle in Q4. Q1 was like, it was just you had to do what it said. Basically, we had to count the number of prefixes of the string s where the length of the prefix mod 3 equal to the count of the distinct characters. So for distinct characters, ideally you would maintain a frequency array of size 26 and like check if this is the first occurrence of the character, but since the constraints were fairly low, you could just like force stuff in a set and it would pass. Even like the runtime, it gave a decent runtime since the constraints were very less. Q4 also, just since the constraints were small, you can just check every subarray and check if it fulfills the condition. I was like, after the contest, I was thinking like, how would you solve this for like, let's say less than equal to 1e5, but I couldn't come up with some solution for this. So I don't think it's like possible for a larger constraint. Yeah, so these two problems were fairly like, you just had to do what it said, so there's no point going over them. Q3 was kind of interesting. Like I solved it in a suboptimal way, but like there's a shorter code for this as well. So first of all, like we are given a vector of strings. The total size, the sum of all the strings is less than equal to 1e5, the sum of all the lengths of the strings, and yeah, only lowercase English letters. So here what you have to do was, basically in the string, let this be the vector of strings. There will be two strings here. Let this one be at I and let this one be at let this one be at I and let this one be at j. So here, if these two strings, they are similar, if we can transform I into j by performing a Caesar shift, and a Caesar shift is like taken from the Caesar cipher, where we shift every character some like k steps ahead. So like a becomes, if k is 1, then a will become b, then it becomes c, and so on, and once it becomes z, it will loop around to a. So like here there is some sort of cyclicity, so we can think in terms of mod 26 for the characters. So my first observation here was, obviously this shift can't append or remove characters, right? So I split it based on the number of characters in every string. This is not required at all, because like once we look at the second step, this becomes implicit. So like assume we did do this, we split them based on the number of characters. So here, let's say we have, for example, AB and then we have BC. We had to count the number of similar strings, right? So assume if to make the count easier, if we normalized every string such that its first character is A. So here, if we force this to be A, that means we are subtracting every character in the string by 1. Like let this be D as well, and then this will be E. So we will subtract every character by 1 if we force this to be A. So this becomes A, this becomes B, and this becomes D. And then we can see that they are matching. So this wouldn't need to be normalized if there were some like larger case, let's say C, not C, wait, D, C, and F. So to normalize this to A, this will get reduced by 3, this by 3, and this by 3 as well. So this becomes A, because we are normalizing it to A. This becomes Z, because this is cyclic, we are going back. So C will go back to Z, 3 steps back, and F will become C. And since this is not matching, and then this is just like counting the number of pairs with this. So this was the implementation. This is actually, this part is not required at all. You can remove this. We can take this out. And then this is just words. 1 second. Yeah, this should work as well since we are using a map to check this stuff. The length will get checked implicitly, right? Yeah, see, this is working as well. It is slightly faster since I'm not doing the pre-processing based on the size, but yeah, it won't matter much. So Q4, my solution is kind of ad hocish and different, but it works. So like basically my first idea was, which gave me the wrong answer. You can again like check why I followed that idea if you look at the live solve. But basically the problem states that given an array of size n with value n is less than equal to 105. Why am I writing the constraints here again? N is less than equal to 105, the values are less than equal to 109, and then we are given at most k operations, and in every operation we can increment value by 1. So k is less than equal to 109. We need to select m elements from this subset from this array, and then have to return the maximum. We have to select m elements such that we can make a maximum and of those elements after performing this operation at most k times. 1 sec. Yeah, okay. So like for these bitwise type operations, since the function here is to result the maximum value, right? So if we observe first of all, since all the values are less than equal to 109, even the increment value is less than equal to 109, we won't deal with more than 31 bits. So like the bits we'll be dealing with will be from 0 to 31. So like this is the first thing. Like even in the worst case, if somehow the value is 109 and then when we add 109 to it, the value won't exceed the 31st bit. The 30th bit, sorry. 31 bits, 0 to 31. The 30th bit, it won't exceed this. And another observation here is, like, if you look at the number bitwise, this is the LSB and this is the MSB. If you look at the number bitwise, the bit at the ith position has like more contribution, has more weight than the sum of all the bits from the 0 to the I minus first position, right? If we assume, like, let's take some number. There's no need to take a number, only weight. Like if we look at the weights of the bits, this is 1, 2 power 0, then 2 power 1, 2 power 2, 2 power 3, 2 power 4, right? If we look at the fourth bit, which is 16, and then we add all these values, it's always less than 16. So since we want to maximize the value, we had to maximize the AND, right? So we would want this to, if we are able to set somehow performing this operation, this increment operation, if we can set the bit at the ith position instead of some like arbitrary bit at a position less than I, then it's optimal to do so, since its weight is guaranteed to be more than the sum of all the weights here. So this gives us the intuition for going from MSB to LSB. Now here, like, let's say we had to select some m elements. I'll make a proper example. I had it in my notebook. Yeah, okay. So let's consider the example they've given only first. 312, right? So I'll write the numbers in their binary representation. So this is 0, 1, 1 is 3, 0, 1, 0 is 2, and then 0, 0, 1 is 1. We'll come from MSB, which is some like, let's say 30th MSB, to the LSB, which is the 0th. So we are at the second bit right now. Yeah, second bit. So the total weight here is 2 power 2, which is 4, right? So now first we try to set this bit, and again we want two elements. So we have k is equal to 8 operations, and we have m is equal to 2 elements to select from here. The first step is to see, like, let's calculate some cost. Obviously, like, again, if we can set this here, then it's good. We'll set it and we'll move ahead. Now, if we move ahead, we would want to go ahead with the maximum possible cost, right? We want k to be as large as possible, so we can repeat this operation again, since this will be the next highest available bit to us. So this gives us the second iteration of minimizing the cost. Now, while minimizing the cost, we notice that to set this bit, the result for after setting this bit will make this 100, right? So to set this bit, it would require this one step, since it's 4 minus 3. This isn't binary. 4 minus 3 is 1, 4 minus 2 is 2, and then 4 minus 1 is 3. For setting this bit, this will require 1 cost, this would require 2 cost, and this would require 3 cost. But we only need we only need to select 2 elements, since the size is given to us as 2, right? So we select the 2 smallest costs, we set this bit, and the values become 100 and then 100 again. Since we have set this bit and we have performed 3 operations, so k becomes 5. And this is discarded because we wouldn't need it after this. We only wanted 2. Now going on to this bit, we just repeat this operation again. Since this is now basically a sub problem, right? You solve this problem from you starting from this bit. So this sub problem gave me the intuition for using this, solving this recursively. This can be done without recursion, but like the sub problem was very natural, so I implemented it recursively. There are some edge cases which need to be handled here. I'll discuss it during the implementation itself. So this is just I'm setting the indices. I'll show you why I'm doing this afterwards. So I pass a recursive function which will consider the nums array, obviously, which is the input. The indices which we have, I'm going from the max bit, which is 30, and the current available cost budget, the number of operations we have, okay. And at the end, I'm returning the result. So here when we okay, so this is, I'm just setting the value of m. Obviously, if no bits are available, you return 0. Else, I'm choosing the current bit. One left shift bit is this only, like the weight of every bit, and this is the current mask. Now I'll show you where this mask is used. Assume this was some example given to us, 0, 1. This example helped me during the contest itself to debug the solution, like why my binary search was not working and why this solution worked. Okay, so we have solved till here. Now we are at this bit. Right, I'll mark the bits as well. And let's say m is equal to 4 for us, and we have some arbitrary k, it doesn't matter. M is equal to 4. We want 4 values. Now, as we can see, to set this bit is already set in all of these numbers, right? So the cost will be the cost for all of this would be 0. So again, to calculate the cost, what we have to do is we have to select a mask of these bits. So this would be, if I am at the ith bit, the mask would be I plus 1, left shift 1 by this, and then subtract all of this by 1 to give us a mask where all of these bits are set. And then we AND it with the, one sec, the current, all of these bits are set, and then when we will AND it with the current number, and then we subtract it from the current weight which we want. So but since this bit is already set in all of these numbers, the cost for all of this is 0, but we have to select 4, and the cost of all of this is same. So the major thing which I took time to solve during the contest was deciding this tiebreaker. If obviously you wouldn't choose the value arbitrary, right, since these numbers are different and later on they can affect the answer. But one thing is for certain, since we are able to set this bit, since it's already set in all, in the result as well this bit will be set. So what I did here was, since this bit is guaranteed to be set now, I set it here, and then I passed it in I passed the values from the next bit onwards as a sub problem, the recursive sub problem, and then after returning the value, I set this bit, because once this bit is gone, the next problem wouldn't care about this, and the scope is relevant to this index only, to this bit only. So we set it here itself. So we ignore this, we go on to the next bit. Now here we can observe we wanted 4 and the minimum cost is provided by these 4, so we discard this. So now the concept of discarding values comes as well, and for this, instead of discarding, I am passing the indices which are relevant. So this was the IDX, the indices array which I was talking about earlier. This contains the current indices of nums which can be operated upon, are possible options for the optimal solution. So again we select these 4. So this is how the values are being selected. Okay, from this here, from this we try to find the cost to set m. Let's say this was to set this bit, we weren't able to satisfy the cost because let's say k was very small. So here we won't try to set this bit. We'll just say don't set this bit. So no, like here also the one left shift bit operation will be done. Here we won't set this bit and pass it to the next, from the next as a subproblem, and it will return whatever value it is, and then this will return it here, and then this will return it here, and this will set the bits as well. So this is what I did. I first calculated all the costs and I pushed them in a vector which is a pair where the primary key is the cost and the secondary key is the index. Since after doing this operation I'll have to modify the values in the vector as well, right? So and then I sort them since I want the smallest cost. I find the total cost, the total current cost if I am to set this bit. If the current cost is outside our budget, let's look at the other case first. We'll consider all of these indexes again, and then the next k, since we won't perform any operation, the k remains the same, right? So I just pass this recursively, the next set of indices which is the same as the current set, and the next k which is the same as the current k, and bit minus 1 because obviously we are considering from the next bit, and since we are moving from SP to LSP, the next bit would be bit minus 1. Now this is the more interesting part. If we can perform the operation, obviously k will get reduced by the cost first of all. Now the max cost with us, the available with us would be the cost of, let's say, let's say after doing this I have some costs. How do I delete this? Okay, after doing this I have some costs. These are sorted from low to high obviously since we want the smallest cost. So this is the cost, this is its relevant index. I'll just put some arbitrary indices here. 0 and then 2, 1 and then 3, 4 and then 5, 4 and then 5, 4 and not 5, 7, 4 and then 8 and then 5 and then 9. This is the cost and this is the index. Now let's say we wanted to select some 5 elements from this. The thing here is these 3 are guaranteed to be selected since they are the smaller costs. With the 4 costs there is some issue like who to select, right? So what I did was prematurely we can select all of this with the maximum possible cost. So if you look at the fifth value, if we were to select m, so m was 5 here, so m minus 1, so fourth value it's 4, right? So till 4 we will select all of the costs and then push them in the next index for future consideration. Push these indices for future consideration, which is what I did. I got the cost and the index. If the cost is greater than the max cost was this, then I break. Like going to 5, we don't want this, we want the smallest costs. Else I update the value in the vector itself, the actual vector. Since I'm performing these cost operations, the value of num_i becomes num_i plus equal to cost, right? And then I push them in the next index for the next call. Now since this bit is being set, since we can perform the operation, this was one left shift bit, we set this bit and then we OR it with the result which will come from the next bit. And again next k is k minus the number of operations, the next bit is bit minus 1 obviously, and the next index is the stuff we put in this. So this was my solution for Q4. Kind of, it is pretty weird, like other solutions are very small, but this was the idea which I came up with during the contest naturally. And yeah, this is the problem which this problem copied. Like it's more or less the same problem. It's weird that they are copying problems from AdCode or regular contests now, but it is what it is. Yeah, okay, yeah, this is the exact same problem, and the constraints are similar as well. Here, like you can see, the constraints are given in this form, so thinking bitwise would be more naturally. For some reason they for some reason they changed the constraints to a decimal format instead of this, which is again weird, but whatever. All right, yeah, this, let me know if you guys require any further clarification with this problem. My solution is weird, I admit it, but I guess my explanation should suffice. All right, thank you, I guess.
much, Ravili.